G'day again. This is Ron, VK2DQ, and in this tutorial we're going to be discussing antennas and transmission lines, tutorial 26, and you'll be able to test yourself for understanding of this tutorial with drill number 20. Most of you will be familiar with coaxial transmission line and parallel line, but I thought I'd just give you a little tiny bit of revision before we go on. On this slide you can see an example of coaxial lines. Coaxial lines are unbalanced lines because the braid of the coaxial line is earthed, and it is the braid that stops the transmission line from radiating. That braid would go back to your transmitter and be earthed to the chassis of your transmitter. And parallel line is shown here connected to an antenna. Parallel line is when we have two parallel wires separated by insulators, and parallel line, believe it or not, and I'll hope to convince you by the end of this tutorial, is the best type of transmission line you can use for your amateur radio station. The reason being is that parallel line is very, very low loss. Parallel line can withstand high SWR. In the 50s and 60s, radio amateurs mostly used parallel line, and in those days they didn't have SWR meters. They didn't need them because they didn't care what the SWR was on a parallel line. Standing waves on a parallel line don't increase the losses of the line significantly. However, a coaxial line does not withstand standing waves very well. When you have standing waves, you have greater voltages and currents than you would normally have, and with coaxial lines, the presence of standing waves can significantly or even greatly increase the line loss. With parallel line, on the other hand, the SWR and standing waves is just simply not an issue. With parallel line, currents that flow on one side of the line flow in the opposite side of the line in the opposite direction. And this is why parallel line is called balanced line, because the currents in each side of the line are equal and going in the opposite direction. That means the magnetic field and electric fields that these currents produce cancel out, and that's why parallel line does not radiate as long as you keep it balanced. You can't run parallel line if you had remember the old TV antennas? They used to be up on a metal pipe, and they would put standoffs away from the metal pipe, because if you put the parallel line near the metal pipe, one side of the line will have more capacitance between it and the pipe than the other side of the line, and it would be unbalanced. So the parallel line was fed up through standoffs and then connected to the antenna. Parallel line is very, very good low loss line. The problem with parallel line is you must maintain its balance. You can't have one side of the line experience something like a metal pipe or the shed of a roof or whatever without the other side experiencing the same. If that is the case, then the currents in each side of the line will be different and the line will radiate. And we don't want that. We don't want transmission lines to radiate. The function of a transmission line is to transfer energy from your transmitter to your antenna without radiating. It's the job of the antenna to radiate. So with parallel line you have to be very careful to keep the line balanced, and that means keeping each side of the line with the same worldly experience. If you will recall the old TV transmitters, what they used to do is twist the line about every 6 inches. I've not shown a real good twist there, I'm not a great drawer, but they would actually just twist the line so that about every metre of the line would have about 4 or 5 twists. And the idea there was to expose each side of the line to the metal pole. Here's the pole, and by twisting the cable we would maintain the balance of the line, because there is a capacitance between each side of the line, and if that line was just run up straight like that, then the capacitance would be different between each side of the line and the pole, and the currents would be unequal in the parallel line, and that would mean that the parallel line would radiate, and that's something we never want transmission lines to do. Coaxial lines, on the other hand, don't radiate. It doesn't matter how you install them, because the coaxial shield around the center conductor prevents any radiation from the cable. Therefore you can bury it in the ground, run it down wall cavities, do whatever you like with it, and it won't radiate. However, the downside is that coaxial line has far more attenuation than parallel line, and also if you're keen, and it's not hard, you can make your own parallel line. It's not part of the syllabus. I suppose I should tell you why we don't want transmission lines to radiate. There are 2 reasons. First of all, we're going to have radiation in our amateur station if our transmission line radiates, and also it means that our radiating transmission line is going to be closer to neighbours, because the transmission line is going to come down from the antenna and back into your house, and that means that the radiating line could be very close to a neighbour, and that could possibly overload their television set or something like that and cause interference. That's one reason why we don't want parallel lines to radiate, or any transmission line to radiate. The other reason is that if the transmission line radiates and you connect it to an antenna, the antenna radiates, and the radiation from the transmission line and the antenna will mix, and you will get a radiation pattern from your antenna that you're not expecting. If you've got a dipole or a Yagi antenna and your transmission line's radiating, then that will modify the radiation pattern of that antenna, and it won't perform or behave as you would have expected it to. The other thing you should know about parallel and coaxial lines is it is the dimensions of the cable or the parallel line which determines the characteristic impedance, and I'll talk a little bit more about the characteristic impedance shortly. As you know, the characteristic impedance of coaxial line is generally about 50 ohms. The reason why it's 50 ohms is the transmitters have a nominal internal impedance of 50 ohms, and that means that most transmitters should be connected to that impedance of 50 ohms. So we make radio transmission lines 50 ohm impedance. We can make other impedances other than 50 ohms, but 50 ohms is the best impedance for low loss and power handling of radio transmitters. That's why we have 50 ohm line, and the manufacturers of transmitting equipment make the power amplifier of the transmitter 50 ohms so that we can get maximum power into that line. A little bit more about that later on. Right now it's the dimensions of the line, the spacings between the center conductor and the braid, the type of dielectric used, the diameter of the center conductor, the diameter of the braid. With parallel line, it's the distance between the lines and the size of wire used in the line that determines the characteristic impedance. There are equations for all of that, but you don't need to know them for the standard assessment, so I'm not going to be giving them to you. There's one other thing I wanted to mention before leaving this slide, is that most of our coaxial cables are called RG something. RG 58, for example. The RG stands for, and you don't need to know this, it's just an interesting fact, stands for radio guide. Coaxial cable was invented during the Second World War because it was too difficult to run parallel lines on metal battleships. And so the US Navy developed, and probably the British as well, and if the truth be known, probably others, they developed coaxial cable so that it could be routed around the metal battleships without becoming unbalanced. Let's talk a little more about this thing called characteristic impedance. Characteristic impedance, the symbol for impedance is Z, and ZO is the symbol for characteristic impedance. I've got a transmitter, I've shown it as an oscillator. That's a radio frequency transmitter, and I've got a transmission line. Let's imagine that this transmission line is of infinite length. Goes on forever. We couldn't build such a line, but we can build it in our heads. So we could actually transmit into this line even though it's open circuit. And the reason why we can transmit into an open circuit is the wave is never going to reach the end of the line. If we did that, and if we put ammeters in series with the line all the way along, and for our purposes we'll assume that this line doesn't have any loss. So these are ammeters in series. Ammeters always go in series. So they're measuring amps. And we'd put voltmeters across the line as well. I'll just draw them like that. It's easier for me. They're voltmeters. So we transmit into this line, which is infinitely long, and then we read these ammeters and voltmeters, and we find that all the ammeters, because it's a lossless line, measure the same thing. All the voltmeters measure the same thing. And let's suppose, for example, what we measured was 100 volts from all the voltmeters and 2 amps from all the ammeters. Then we've got a voltage current ratio there, and you'll remember that R, in Ohm's law, R equals E over I. Well, that's also the same equation for impedance. Z equals E over I. So suppose on this infinite line, all of our voltmeters measured 100 volts. And all of our ammeters measured 2 amps. Then the characteristic of this impedance of this line, the ZO of this line, would be 2 into 100 equals 50 ohms. That's what characteristic impedance is. Of course, in practice, we can't have infinite lines. But if we wanted all of these voltmeters and all of these ammeters to continue to read 100 volts and 2 amps, we would have to terminate this line in a resistance equal to its characteristic impedance, and that would be 50 ohms. So that resistance would be 50 ohms. If we did that, then all of these ammeters and voltmeters would stay exactly the same. The wave would travel down the finite line now. They would still measure 100 volts and 2 amps. They're arbitrary figures, but the ratio is 50. That's not arbitrary. And when the wave reaches the load, nothing unusual is going to happen because the load is also 50 ohms, and it's going to dissipate all of the energy that arrives at the load in the form of heat. And if the load was an antenna, then all of the power and it was 50 ohms, all of the power arriving at the load would be radiated. However, if it was not 50 ohms, if it was a 100 ohm load, then some of the power arriving at the load would be reflected back. So now we've got two waves. We've got a forward going wave, I'll just call that F, and we've got a reflected wave, and that's going to upset all these ammeters and voltmeters. We're going to have what's called a standing wave on the line, an interference pattern between the forward and reflected energies. And that is going to cause much higher voltages and much higher currents in some spot if we had have terminated the line in 50 ohms. And these higher voltages and higher currents caused by standing waves are going to increase the losses of the line, particularly if we're using coaxial line. The standing wave ratio is the ratio between the characteristic impedance of the line and the load that it's terminated in. If our load was 100 ohms and our characteristic impedance of our line was 50 ohms, then what's the ratio between 100 and 50? It's 2 to 1. So the SWR, the standing wave ratio of these standing waves, would be 2 to 1. If our load was 200 ohms, then the ratio between 50 and 200, not a very nice O, the ratio between 50 and 200, the standing wave ratio would be 4 to 1. We try, with coaxial cable in particular, to terminate the cable into 50 ohms to avoid standing waves and to avoid extra line losses. And don't let anyone else tell you there's anything else bad about standing waves. There are a whole hodgepodge of fallacies regarding standing waves, such as the reflected power comes back and jumps into your transmitter and burns out the finals. Standing waves cause interference. There's a whole raft of fallacies regarding standing waves. Firstly, with parallel line, standing waves aren't an issue. You have to match your transmitter to the impedance of the line, but whatever the standing waves are on the line, it really doesn't matter, because standing waves don't significantly increase parallel line loss. However, they do significantly increase coaxial line loss. So for that reason, we use an SWR meter, a standing wave indicator, to tell us if we've got a match between our transmission line and our antenna. If our SWR is 1 to 1, that means we've got 50 ohm line and a 50 ohm load. And if we have a 50 ohm line and a 50 ohm load, which is our antenna, then we will not have standing waves, because the wave will travel down the line with a current voltage distribution of 50 ohms, and when the wave arrives at the load, it will also see 50 ohms and be totally radiated by an antenna or dissipated by a 50 ohm resistance. If we use coaxial lines of different impedances, or if we are connecting, say, a parallel line to a coaxial line, coaxial line is unbalanced line, parallel line is balanced line. If we were just to connect the two of them together, the unbalanced coaxial line would unbalance the balanced line. So we need a device that will enable us to connect a balanced line to an unbalanced line, and such a device is a balun. It comes from the words balanced and unbalanced, a balun, balanced to unbalanced. Not only, and if we use a balun, that will prevent the coaxial cable, the unbalanced line, from unbalancing the balanced line. The other thing that a balun can do, it can actually do an impedance transformation. So if this was 200 ohm line and this was 50 ohm line, well, there's an impedance ratio there of 4 to 1. And we could use a 4 to 1 balun to connect between those two cables and prevent the coaxial line unbalancing the balanced line. You need to know what a balun is used for. Similarly, if we were to connect an antenna to this line, and let's suppose the antenna was 100 ohms and the cable was 50 ohms, then we could use, at this point here at the antenna, we could put a, well, it would be called a 2 to 1 balun, but it's actually a 1 to 2 ratio, but we normally call it a 2-to-1 balun, and that would give us that impedance match between a 50 ohm line and the 100 ohm antenna impedance, and that would prevent standing waves, and that would prevent unwanted transmission line loss. We're not going to go too deeply into baluns in the standard course. In fact, we're not going to go too deeply into transmission lines and antennas, because they are both very, very deep subjects that go way beyond advanced level. And I would encourage you to learn more later on. But right now, I'm constrained by the standard syllabus. What I will tell you is this. There's a really big fallacy out there that baluns are transformers. You're used to a transformer having a primary and a secondary and a laminated core or a ferrite core. You can make a balun using a mutually coupled transformer. But if we did that, these types of baluns are very narrow bandwidth, and radio amateurs operate over a wide band of frequencies. So we don't use mutually coupled inductors or transformers to make our baluns. We use a different principle. We use transmission line baluns, and I'm not going to go into it. I would just like you to know that there is no similarity whatsoever. There may be a physical similarity, and I think this is where all the confusion comes from, because people look at transmission line baluns and they see what looks like a primary, they see what looks like a secondary, and they see a core and they think it's an ordinary transformer. It is not. Transmission line baluns do not have a primary. They do not have a secondary. They do not have a turns ratio. There is absolutely nothing in common between transmission line transformers and mutually coupled transformers like we'd use in a power supply. We can use them as baluns, but we don't, because they're too narrow band. They're used by people like radio broadcasters who are transmitting on the same frequency. They would use a transformer type balun like that. But the baluns that we use in amateur radio are called transmission line transformers. They use the principles of transmission lines to work and not the principles of mutually coupled transformers. SWR is simply the ratio between the characteristic impedance of the line and the impedance of our antenna. Whatever's the largest goes on the top, so if ZL was larger, it would go on the top. So if our load was 400 ohms and our characteristic impedance of our line was 50 ohms, then the standing wave ratio, SWR, would be 8-to-1. As radio amateurs, normally with coaxial cable, we're looking for the perfect SWR, which is 1-to-1. Actually, the difference between 1-to-1 and 1.5-to-1 is insignificant. So anywhere between 1-to-1 and 1.5-to-1 should be considered an ideal SWR. Although radio amateurs, some of them, will muck around for days reducing an SWR from 1.5-to-1 to 1-to-1, whereas 1.5-to-1 is so close to 1-to-1, it's a non-linear scale. It's almost one and the same thing. So if you can get your SWR down to 1.5-to-1, that's fine. You're a mug if you try and do it anymore. But a perfect SWR, of course, would be 1-to-1. Electromagnetic radiation in free space has a velocity of 300 million meters per second. When an electromagnetic wave is made to travel down a cable, the velocity of propagation slows. And this slide shows you different types of cable and how much the velocity has slowed. The cables are given what's known as a velocity factor, and the velocity factor is simply the relative speed of light. For example, pretty ordinary, typical, and this is the one you'll be dealing with most of the time, coaxial cable has a velocity factor of 0.66. That means that the speed of propagation down a coaxial cable is 66% of light velocity, 66% of 300 million meters per second. And you'll notice that parallel line has a higher velocity factor than coaxial cable. There's the 300 ohm ribbon cable, for example, has a velocity factor of 0.8. Why that's important is because there's going to be times when you need to calculate the wavelength, or you'll need to get a piece of cable and cut it to a particular wavelength. Well, when you do the calculation for wavelength lambda equals 300 over frequency in megahertz. And the reason why the frequency is in megahertz and not hertz is because we've converted that from 300 million to 300, and we make the frequency megahertz. So that's a really good equation to remember. In fact, you need to remember this equation. But if I was going to work out how long a wavelength of coaxial line was, I can't use this velocity because that's the velocity of light in free space. So I would have to, if I wanted one wavelength of cable, say coaxial cable at 10 megahertz, I would say 300 divided by 10 and multiplied by the velocity factor would give me the wavelength of that cable. I'm not going to do the sum, I don't need to, and you won't have to do it in your exam, but you will need to know this equation because that's the root equation for working out the dimensions of most antennas. So it'd be a good idea if you commit that one to memory, and it should be on your formula sheet in your assessment anyway. The other thing you need to know about transmission line is the losses not only increase with increasing standing waves, but they also increase with frequency. On this chart, we have frequency on the x-axis increasing towards the right, and we have attenuation on the y-axis in decibels increasing upwards. Have a look at some common cables. Here's RG8. Here's a group of very, very, very common coaxial cables. RG8, very popular for amateur radio. And just, for example, have a look at what the loss would be at 10 megahertz. 10 megahertz, we've got approximately 0.6 dB loss, which is not a lot of loss. But let's go up to 100 megahertz, and the loss is 2.5 dB, and that's a lot of loss. That's almost half your power. 3 dB is half your power being lost, so you wouldn't use these cables over 100 megahertz. You'd probably use these on HF frequencies only. The other thing I'd like you to look at is look at the open wire. This is open wire, half-inch spacing. It doesn't even get on the chart up to just below 15 megahertz. And look at, say, the losses at 200 megahertz. That's pretty much just over 0.4 of a dB. So open wire transmission line is far superior than coaxial cable if you're willing to make it yourself, or you can buy it, and to install it correctly. You're going to be able to make an antenna that'll operate on any amateur radio band. I'm just going to clear that screen. I hope you can see that. It's a little bit fuzzy. I'll try and put a clearer version of that graph in the document folder of your DVD-ROM for you. because we're so concerned about standing waves increasing coaxial line loss and nothing else, there's nothing else bad about them, we'll often use a network such as this. It's a antenna tuner. The output of the transmitter could have this in it, and you could also have an external tuner as well. And when used at the transmitter, what this tuner does is match whatever this impedance is, Z1, to this impedance, Z2. So that could be going to your antenna, and this is going to your transmitter. You could have a transmission line on here, and your SWR meter would be placed in this location, and then your transmitter, so an SWR meter there, and you would look at your SWR meter and you would adjust the three controls. The inductor is sometimes variable, or sometimes it's got tappings on it, so you can switch to different positions, and that's sometimes labelled band. So you might have the 10 meter band, the 20 meter band, you might have those switches on it. But basically the antenna tuner is just adjusted. You adjust each control, each capacitor, until you get minimum SWR. And really with an antenna tuner you can adjust it to get an SWR which is 1:1. It's quite easy. And also the output of your transmitter itself, the transmitter, in the output of the transmitter there is a network similar to that to adjust the impedance of the transmitter to what it's expecting, and that's 50 ohms. That's called a pi network because it looks like the Greek letter pi, and it's a very common network for antenna tuners. It's also a low pass filter. We'll be talking about filters later on, and when we do you'll recognize the antenna tuner as a low pass filter. So one of the benefits of having an antenna tuner besides matching impedance is that it'll give you a low pass on your transmit frequency and attenuate any spurious emissions or harmonics which are above your transmit frequency. Most amateur radio stations require a good antenna tuner if you're going to be operating on multiple bands. Now let's have a talk about some of the antennas that you're going to need to know about for the standard assessment. Before, and I've just rotated this image, before we were discussing if this was a transmission line it won't radiate. If it was a parallel line it won't radiate because on each leg of the line the currents are going, they're equal and they're going in the opposite direction. So any magnetic or electric fields they generate are cancelled out by one another. With coaxial cable it's the outer braid that prevents any radiation from the transmission line. But what if we got some scissors and we cut down the centre of this parallel line? Cut it down, say we cut it down to about here. And then, because the insulator's cut, I can now fold one leg of this transmission line over this way, so it will be out like that. So this here has now been folded down like that, and let's do the same thing to this one. We certainly have unbalanced this transmission line. It's a balanced transmission line and we've horribly unbalanced it. So there will be radiation now from these two wires which were once part of the transmission line. And if those two wires are a half wavelength long, that is called a dipole. And the impedance of a dipole at the feed point, that's this point there, is approximately 70 ohms. And you should remember that. There are a few antennas you need to know a little bit of information about. Firstly, we've just discussed the dipole. It's a half wavelength long. That's our feeder. I'm using parallel line, but it could be coaxial cable. But if you did use coaxial cable to feed a dipole, coaxial cable is unbalanced line. A dipole antenna is a balanced antenna, so we would have to place a balun there. You should never connect coaxial cable directly to a dipole. It should go through a balun. If you don't, the coaxial cable will radiate. So that's the dipole. And you need to remember that it has an impedance of about 70 ohms. The other antenna you need to know about is the ground plane antenna. The ground plane antenna is a quarter wavelength long. The dipole is a half wavelength. Lambda is the symbol for wavelength. That's lambda, Greek letter lambda. The quarter wave vertical antenna is a quarter wavelength long, and it normally has radials, and if it has radials, and I wonder if you can see it's just half of a dipole, because if I had a dipole and I folded one leg up, I would get this. So if this was a vertical dipole and I folded it up to that shape, an L shape, this is the radiator, that's called the radiator, and this is called a radial. And normally we put at least 3 radials or more on a vertical ground plane antenna. So we'd have another radial coming out here, we'd have another radial going out there, and if you look side on you'd only see that. And they're all a quarter wavelength long, and they're horizontal. I'm a bad drawer, so it doesn't look horizontal, so this is a side elevation, and they're all horizontal. If we do that with a quarter wave ground plane antenna, the impedance there is around about half that of a dipole. That's no surprise, is it? Because it is half a dipole, and that's around about 36 ohms, which is still not real good for 50 ohm cable. So if we get our quarter wave vertical and slope the radials down from the horizontal, that's the one behind, so this is the horizontal here, the angle here is about 45 degrees. If we do that, it's not surprising, because we're returning closer to a dipole, we're going to increase the impedance from 36 towards 70. If we folded all of these radials down and clumped them together, we would have a vertical dipole. But so obviously the impedance at 45 degrees is going to be somewhere between 70 and 36, and it just nicely turns out to be about 50 ohms, which is a very good match to 50 ohm transmission line. Okay, let's have a look at the Yagi antenna. This slide is of a 3-element Yagi antenna. Now a Yagi antenna is really just parallel dipoles. This is the driven element. This is the element that we would connect our coaxial cable to and take it down into the station to our transmitter via our ATU. So that is called the driven element. That's the one we're giving the energy to. And the other 2 elements in a 3-element Yagi are really just 2 more dipoles. Another dipole, I've accentuated the sizes here a little bit too much, but I'll explain the dimensions shortly. The one in front is called the director, and it's 5% shorter than the driven element. And the one behind is called the reflector. That's 5% shorter for the director. I should have written that in. Not much good just putting 5% up there for you. It's 5% shorter than the driven element, and the reflector is 5% longer. The driven element dimensions can be found from, it's a half wavelength, so the length of a dipole, L of a dipole, a wavelength would be 300 over frequency in megahertz. That gives us one wavelength. We only want a half wavelength, so we need to multiply that by a half, or 0.5. And we also need to reduce its size slightly because this is a free space wavelength. On Earth, because there is because of end effect of the driven element and because of a slowing down of the propagation of the wave through a wire, a conductor rather than space, we need to reduce its size by 5%, and we do that by multiplying by 0.95. So the driven element is a half wavelength long, a little bit shorter than the free space wavelength. That reduces its length by 5%. This gives us a half wavelength because this calculation gives us a wavelength. So 300 over frequency in megahertz gives us a wavelength in free space. Multiplying by 0.5 gives us a half wavelength in free space, and reducing that dimension by 5% by multiplying by 0.95 gives us the length of the director in a 3-element Yagi. The driven element, I should say. The director is 5% shorter, the reflector is 5% longer. The impedance you don't need to know, but it's fairly obvious. Imagine if you were putting resistors in parallel. If you had two 100 ohm resistors and you put them in parallel, you would get a total resistance of 50 ohms, and I hope you were able to answer that. Well, these dipoles are in parallel, and the impedance of one dipole is approximately 70 ohms, and we've got 3 of them in parallel. They're not connected electrically to each other. The reflector and the director get their energy from radiation from the driven element. So when the driven element radiates, the reflector picks up some of that energy and it radiates as well, and the director picks up some of that energy and it radiates as well, and that's what gives the Yagi antenna its directional properties in that direction. So we've basically got 3 dipoles in parallel. These are called parasitic elements because they're not directly connected to the feed line. They actually suck or draw their energy from the driven element. They're parasites, so they're called parasitic elements. And our impedance of 3 dipoles in parallel is going to be roughly 3 into 70, whatever that is. And the more elements you have, the lower the impedance is going to be. And so we normally have some sort of special matching device there to match to the 50 ohms of our feed line. The typical matching device is called a gamma match, but again, you don't need to know that for the standard, and I don't want to prolong this course for you. The other thing you need to know is the current and voltage distribution on a dipole antenna, and this is the dipole antenna. This is where our feed line would be, going to the transmitter via an ATU and SWR meter. And this is a quarter wave vertical antenna. It could have radials, or it could be mounted on an insulating plate on the ground. But that's a quarter wave antenna. I wonder if you can see that if you take half the dipole and rotate it around clockwise, say you took this part of the dipole and rotated it around, you would get the quarter wave. So you really only have to remember one of these. I'm just going to explain what it all means. Not how it happens, that's a little bit too much for us to go into. But if we were to put ammeters along a dipole, all along its length, we would measure maximum current at the feed point. This is the feed point, this is where it's 70 ohms. You can end-fed a dipole. In fact, you can off-center-fed a dipole as well, but we're only interested in a center-fed dipole. So the impedance is 70 ohms, and that's going to our transmitter. So if we were to measure the currents flowing in this antenna, we would find there's maximum current at the feed point and 0 current at the ends. So that graph is a visual representation of how much current is flowing in this antenna at different points. At the ends of of a dipole antenna, there's virtually no current at both ends, and in the center there is maximum current. And between the center and the end, the current begins to fall off. Voltage is maximum at the ends of a dipole. That's voltage is maximum there and here. So voltage is maximum at the ends and falls off to almost zero. Not zero because it's 70 ohms. Now if you think about it, this is an open circuit. And since Z equals E over I, how much I do you think you would have here? Very little. You have very, very little I, so you've got some pretty crappy I, isn't it? You've got very little current flowing at the end, a lot of voltage, so you're going to have a big impedance. If you've got a large number in the numerator there and a small number in the denominator, this is going to be a big number. So you've got a high impedance at the ends and a low impedance of 70 ohms in the center. That might help you remember that a dipole has high voltage on the ends, low voltage in the middle, has high current in the middle, and low current on the ends. And a quarter wave vertical is just half a dipole. So if we took this part of the dipole and just rotated it around, we would get a quarter wave. And similarly, we have high voltage at the ends and low current. And a quarter wavelength back, we've got high current and low voltage. And that's about 36 ohms impedance there. It's a low impedance because we've got a lot of current and very little voltage. And you need to remember, you may have to identify those diagrams. I'll just take all my rubbish off. What you could get in your exam is either one or even both of those diagrams and be asked what it is. And that would be a dipole antenna. Or you could be asked about the current distribution or the voltage distribution of a dipole. And if you remember, high voltage at the ends, low in the middle. Low current at the ends, high current in the middle. And a similar situation for the quarter wave vertical antenna. Be a good idea if you remembered those. Well, I think we're just about ready to start having a look at our questions. There isn't a lot of depth to antennas and transmission lines in the standard. So I think we will start having a look through some sample questions and see if we've forgotten to tell you anything at the same time. Rightio, let's do some trial exam questions. Section 20, antennas and transmission lines for the standard course. Your drill software to test you on these questions is drill number 20. And sometimes you might even be able to skip over some of these tutorials and just go to the drills if you know it, and that will save you some time as well. Let's have a go at this one. 20.1. The characteristic impedance of a transmission line does not change with frequency. It's not like an ordinary impedance. It's not like the impedance of a resistive and inductive and capacitive circuit. Characteristic impedance is that behavior of transmission lines where the voltage and current distribution in them as a wave's travelling through them settles into a particular ratio, an EI ratio, and Z equals E over I, that's impedance, and that's called the characteristic impedance. 20.2, loss in a transmission line is minimized when the line is terminated in its characteristic impedance. If you've got 50 ohm line, then the terminal impedance of the antenna ideally should be 50 ohms as well. 20.3, and this is the only velocity factor you're going to have to know. The velocity factor for commonly used coaxial cables is approximately 0.66. 20.4, coaxial cable can be described as an unbalanced transmission line. I'm not commenting on the others unless they're close enough to the right answer to confuse you. 20.5. The impedance of a transmission line must match both the antenna and the transmitter output impedance in order to obtain maximum power transfer to the antenna. If we don't have matched impedance, we have reflected waves on the transmission line which combine with the waves coming from the antenna, and we get an interference pattern of waves on the transmission line called standing waves, and they increase our transmission line losses substantially. Particularly once you go above 2.5 to 1 SWR, transmission line loss becomes a little bit miserable. 20.6. A balun is used to match unbalanced coaxial lines, connect two coaxial lines, prevent radiation of undesired signals. No, match unbalanced transmission lines. So if you had two different coaxial lines of different impedance, although the common one is 50 ohms, you can get 90 ohm impedance cable, and if you wanted to join those two cables together, you would use a balun. If you wanted to connect balanced line to unbalanced line, parallel line to coaxial line, you would use a balun, just the same. .7. One function of the output stage coupling network of a transmitter, and I've shown that there. That could just as easily be the schematic diagram of an antenna tuning unit as well, but you have a stage similar to this in the output of a transmitter, and its function, we talked about it being a filter, and it's a low pass filter. Not only can it match impedance for us, but it can reduce harmonics and other spurious emissions above the transmitter frequency, because a low pass filter passes low frequencies and stops high ones, and our harmonics are on multiples of our transmit frequency. So if we're transmitting on 14 megahertz, our second harmonic would be on 28 megahertz, and the ATU or output coupling network in the transmitter would attenuate that harmonic substantially. 20.8. When a transmission line is correctly matched to an antenna, the standing wave ratio is never zero. The best the standing wave ratio would ever be is 1 to 1. The velocity factor of the line is 1. That's nonsense. If it's a coaxial line, it's 0.66, and that never changes. If it's a parallel line, the velocity factor is about 0.8. If it's matched, the standing wave ratio won't be very high. So again, we get maximum power delivered to our antenna if our transmission line is correctly matched to the antenna. 20.9. A device used to couple a coaxial transmission line to a balanced antenna is known as a balun. 2010. To enable a single antenna to be used for both transmission and reception, you may employ a changeover relay. Now, if you've forgotten about that, recall when I brought up the block diagram of an SSB transceiver, and it's in the document folder. It's a PDF file. If you have a look at that block diagram of a transceiver, you'll see that there's a relay there which switches the antenna between the transmitter and the receiver. So if you're listening, the relay operates and connects the antenna inside to the receiver. When you press the push to talk, the relay operates and connects the transmitter to the antenna. 2011. The polarization of an electromagnetic wave radiated by an antenna is specified by the direction of the electric field. If the electric field's vertical, you've got vertical polarization. If the magnetic field is horizontal, you've got vertical polarization. Because if the magnetic field is horizontal, the electric field is at right angles to the magnetic field, so the electric field is vertical. Never ever associate polarization with the type of antenna. Polarization has got to do with the radiated wave and the direction of its electric field. It has to be that way because when waves radiate from antennas, they may begin as vertically polarized waves, but as they propagate via the ionosphere, and there are other effects that do this as well, their polarization can change. 2012, the radiation pattern of an antenna is not affected by reflections from the ground. That's not correct because our antenna radiation is affected by ground reflections. Is the same for both transmitting and receiving modes. What that's saying is that whatever an antenna does for you on transmit, it also does for you on receive. If you've got a Yagi antenna with a gain of 8 dB, then it gives you 8 dB gain on transmit, and it'll give you the same 8 dB gain on receive. So you get the double usage out of antennas because their gain works for you both on transmit and receive. 20.313, the standing wave ratio, SWR, on a transmission line is related to the power fed to the antenna to the power reflected back from the antenna. It's not a simple ratio. I'm not going to give you the equation because you don't need to know it, but it's not simply if there's 100 watts going to the antenna and 50 watts reflected, that's not 2 to 1 SWR. It's a little bit more complicated than that, but we just don't need to know it right now. But you do need to know that SWR is related to the power fed to the antenna and the power reflected back, and there's a simple mathematical equation to work out the SWR, or it's simply the ratio between the transmission line impedance and the load impedance. If the load is 500 ohms and the transmission line's 100 ohms, then your SWR is 5 to 1. 20.14, the optimum value of standing wave ratio is 1 to 1. 20.15, the approximate length of a half-wave dipole antenna for 21 megahertz. Well, if you don't know that 21 megahertz is the 15 meter band, then you have to do a bit of a calculation. And if you need to do a calculation, this is what you'd do. You'd say, okay, I need to know, and remember it's a half-wave dipole, so we're after a half wavelength, but a wavelength is 300 divided by frequency in megahertz. And that's 21, not 12. And that is a full wavelength, so we would have to divide that answer by 2. And 20 into 300 is 15, so we can just approximate it. That's why it's called the 15 meter band. And then if we divide that by 2, we get 7.5 meters. Just be careful when you're calculating wavelengths, because here I'll highlight it for you. We're asked for a half wave length. So that's the 15 meter band, because a wavelength is roughly 15 meters long on the 15 meter band. So our dipole antenna would be a half wavelength, 7.5 meters. 20.16, this diagram represents the current and voltage distribution of a half-wave dipole. They've done a little bit different than I did, and they do it both ways. The current's the same. The current is almost zero at the ends and maximum in the middle, and the voltage is high at the end and high at the end here, but they've chosen to draw their graph under the antenna. The only reason they've done that is because there is a phase change in the voltage between one side of the antenna and the other. So it's just as correct to draw the voltage the way I did, or to draw it the way they've done it here. But you need to identify that as a half-wave dipole antenna. 2017, the current at the center feed point of a half-wave dipole, they're asking you what the current is there at the center. It's going to be maximum. 20.18, a half-wave dipole antenna resonant on 20 megahertz would have an approximate length. Well, okay, 28 megahertz is pretty close to 30, so let's call it 30. And let's divide 30 into 300, and we get 10. That's the wavelength, and we want a half wavelength, so we need to halve it 5 meters. (20.19) At the ends of a half-wave dipole, now I'm not even going to read the answers, because I'm going to think about a half-wave dipole. At the ends of the dipole, the voltage is high and the current is low. So let's see if we can find that. Voltage is high and the current is low. And you got that from your graph back here. Remember this? Voltage is high, current is low. Voltage is high, current is low. 20.20, the impedance of a center-fed folded dipole. A folded dipole is 300 ohms. A folded dipole is two dipoles very closely together. Only one of them is connected to the feeder, and the ends of the dipole are connected together. The two dipoles may only be a few centimeters apart, joined at the ends, and one of the dipoles is fed with the transmission line feeder. When you do that, you raise the feed point impedance from 70 ohms to 300 ohms. So you really have to watch for this word folded, because that's a folded dipole. Impedance of a folded dipole. This is the impedance of a standard dipole. Don't mix them up. This is the impedance of a quarter wave vertical. And this is the impedance, 50 ohms, of a quarter wave vertical with radials sloping down at 45 degrees. So you've got the whole lot there. You don't have to remember any others for the standard other than that. A quarter wave vertical with the radials horizontal. Quarter wave vertical with the radials sloping down 45 degrees gives you 50 ohms. Center fed dipole 70 ohms, and a folded dipole 300 ohms. 20.21, the diagram below represents the voltage and current distribution of, it's half of what we had before, of the dipole up the top, so it's a quarter wave vertical antenna. This one would be the voltage, and this one would be the current. At the ends of an antenna, you always have high voltage and low current, because that's a high impedance. An open circuit is a high impedance. 20.22, the impedance of a quarter wave ground plane antenna at its resonant frequency is approximately 36 ohms. It's a ground plane antenna, but they didn't say the radials were sloping down. If they were, that would give us 50 ohms. 20.23, a vertical ground plane antenna operating at 20 megahertz may have its radials lower than the horizontal by an angle of 45 degrees. This raises the antenna feed point, that raises the impedance of the antenna feed point. (20.24) A dummy load. A dummy load is a 50 ohm resistor. A big 50 ohm resistor, usually with a big heatsink on it, and usually immersed in oil or something else. It's a non-radiating antenna. This big 50 ohm resistor can be connected to your antenna so that you can do tests and tuning and maybe repairs without transmitting and annoying people from an antenna. So a dummy load, it's also called an artificial antenna. D is the correct answer, provides the electrical characteristics of an antenna and dissipates power without radiating. When testing a transmitter into a dummy load, that's not right, A is not right. B's not right. The radio frequency signals are converted to heat. The purpose of a dummy load is to absorb all the energy, turn it into heat, and not radiate, so that we can do tests without interfering with other operators. 20.26. To prevent radiation of radio signals when a transmitter is being tested continuously, you would use an artificial antenna, aka a dummy load. 20.27. The length of the reflector element of a 3-element Yagi is usually about 5% longer than the driven element. 20.28. The antenna transmission line is connected to a 3-element Yagi antenna at the driven element. 20.29. In a 3-element beam antenna, the director should be slightly shorter than the radiator. So the shortest element is the director, the longest is the reflector, the driven element is 5% less than its free space wavelength, the driven element is 5% shorter than its free space wavelength, the director is 5% shorter than the driven element, the reflector is 5% longer than the driven element. 20.3. A Yagi beam antenna usually consists of a driven element, a reflector, and an additional element called directors. 23.1. To enable a single antenna to be used for both transmission and reception, you may employ a changeover relay. I think that might be a repeat question. Well, that's it for tutorial 26. Don't forget, you can test yourself with drill number 20. And if you're getting like 85, 90% in the drills, then you're doing very, very well. And you won't have any trouble with your assessment. So cheers for now. I'll see you in the next tutorial. This is Ron, VK2DQ. Thank you for your time and patience with the course. It does work. Keep at it. It'll pay off for you. Cheers for now.